Hi, this is John from Diver's Den. Today I want to talk about nitrox versus air because a lot of times when people are doing the e-learning, they come to me and they don't understand some pretty key concepts, particularly partial pressures and MODs and understanding the gas, physics, and physiology associated with those. So some things I want to talk about specifically are Henry's law and Dalton's law and how those apply to those gas physics and how they affect your physiology. So Henry's law pretty much just states that, if you wanted to put it up on the board, it's solubility equals a factor, and that factor is based upon the gas. It's a solubility factor times the pressure. Well, good thing this isn't college science or chemistry, and we don't have to worry about figuring out how many moles get dissolved in a gas or into a fluid. So what this means is if I have a fluid adjacent to a pressurized gas, a gas can be anything, we'll call it nitrogen, that, and this is a pressurized, we'll say 1 atmosphere, that the number, based upon the solubility of this gas, some molecules or moles are going to get dissolved into that fluid. So that's what Henry's law states. We don't worry about the number of moles dissolved in diving because it's not really relevant for our cause. So we don't care about this, right? All we care about is the solubility is proportional to the pressure. And why that's important is because we know that at every pressure, the gas is going to be the same number of molecules dissolved into our body. Like this fluid is us, primarily our blood, and then that blood gets transferred to our tissues, which is effectively a fluid. Even our bones and things like that, it gets absorbed into our body at different rates, but it still gets absorbed into our body. Okay, so that's Henry's law. So it's important to know that Henry's law just states, hey, if I have a gas adjacent to a fluid at any given pressure, the gas is going to dissolve into that fluid consistently. That's Henry's law. Dalton's law says if I have a mix of gases next to a fluid, that the pressure exerted or dissolved into those gases is going to be equal to the total pressure on that fluid. So if I have 1 atmosphere, and I have atmosphere, and I have gas 1, I have gas 2, I have gas 2 here, right? And it's gonna, the total sum of those pressures is going to be equal to 1 atmosphere. Right, so I have pressure of gas 1 plus the pressure of gas 2 equals 1 atmosphere, because up here is 1 atmosphere. So if I go down to 2 atmospheres, it wouldn't matter. It would still be gas 1, gas 2 is 2 atmospheres. So we went down to there, right? So atmospheres, again, is just another way to measure pressure. It could, atmospheres could be measured in, or pressure could be measured in inches of mercury, which is 760 inches at the surface. It could be measured in 14.7 pounds per square inch. It could be measured in 33 feet of seawater, whatever unit we use, but atmospheres are easy because it's 1, 2, 3, 4, small numbers are easy, right? So say, for instance, we have, let's choose 2 gases. We'll choose oxygen and nitrogen. Nitrogen is an inert gas. Oxygen is not an inert gas. It's metabolized by our body. But nitrogen is not. Nitrogen is inert. It's not used up. It just gets absorbed into our tissues, and then it gets off-gassed by our tissues as we ascend. Right, so it's not used, and that's the gas of concern when it comes to decompression sickness. Right, so say I have 2 gases. I have let's just start with 20%. I have a 20% So we have a partial pressure of PO2 of oxygen of 0.2, right? Because I'm at 1 atmosphere, right? So if I'm 1 atmosphere, this is my oxygen and this is my nitrogen. We'll do oxygen as red, I guess, to make it easier. And nitrogen is 0. And if I'm at 1 atmosphere, make this a little bit cleaner. 20% oxygen. This is a little hypoxic. Our normal breathing air is 21% oxygen, but this is going to make the math a little easier. Okay, so at 1 atmosphere, this is going to be 0.2 partial pressure. So this is the partial pressure of oxygen. This is the partial pressure of nitrogen. Okay, and then my partial pressure of nitrogen would be 0.8. Because at 0.2 plus 0.8 equals 1. If I were to go down an additional 33 feet to 33 feet total to 2 atmospheres, they would have to add up to 2 atmospheres. So in this case, it doubles. 0.4 and 1.6. 1.6 plus 0.4 is 2 atmospheres. It goes down another 33 feet to 66 feet, or 3 atmospheres. 2 atmospheres, 3 atmospheres. It's going to add another 0.2, so 0.6. It's going to add another 0.8, so 2.4. Right, so 2.4 plus 0.6 is 3 atmospheres. Okay, it's going to go down another 33 feet to 4 atmospheres. And the trend continues. 0.8 and 3.2 partial pressures of nitrogen, partial pressure of oxygen, and finally we'll go down all the way to 5 atmospheres. This is 99 feet right here, and this is 132 feet. Right, and then we're at 1 atmosphere, 1 partial pressure of oxygen, and 4 partial pressures of nitrogen. Right, and what kind of controls the rate of nitrogen absorption is the partial pressure of nitrogen. So if you were to kind of graph this, right, this is your percent of nitrogen, or your percent loading in nitrogen, and this is your time, or we'll just say like a really fast gas. So like there's 5 different types of tissues. We'll just say it's like, or there's more than that, but we'll say for a 5 tissue model, like a really fast, soft tissue, like it takes 5 of the half-lives for that tissue, but it looks like this, right? It would look like this as that loads up, but if you went deeper, it'd be even faster, right? If you went shallower, it would be like this. For that tissue to get fully loaded, and your computer kind of cuts you off around like right there for no decompression limits. But that's neither here nor there. But my point is the higher partial differential pressure between this and what is in your body, the faster you're going to on-gas. And contrarily, if your partial pressure of the nitrogen in your body is higher than the atmosphere, the faster you will off-gas. And if you off-gas too fast, that's when microbubbles form in your body, and that's what the bends is in decompression sickness is. So let's look at a gas that's a lot higher. Let's say we're doing a gas that is, the maximum we're allowed to do is recreational divers. It's a 40% oxygen mix. So my O2 and my nitrogen. So about 1 atmosphere, it's going to be 0.4, and then it's going to be 0.6. At 2 atmospheres, it's going to be 0.8 and 1.2. 3 atmospheres, it's going to be 1.2, and then we're going to be at 1.8. At 3 atmospheres, it's going to be 1.6, and we'll be at 2.4, and then At 4 or 5 atmospheres, it's going to be 2.0, and we're going to be at 3.0. So if you examine the nitrogen column here, you'll note that this number here and this number here are identical. So if you're diving in these two mixes exactly, it would be like diving on a 40% mix at 99 feet is the exact same as far as nitrogen exposure is concerned as diving at 66 feet on a 20% mix. That's great, right? So why would you so that's how we, manage our nitrogen. Like that's it. Why would we not do like 100% mix, right? So we'll get to that in a second, right? So if you're wondering how we manage our nitrogen exposure, there's a tool for that. We call that no decompression limits, right? That's a function of our depth and our time. The deeper we go and the longer we stay, that reduces our partial pressure of our nitrogen and our time exposed to that partial pressure of nitrogen to our body. And that's why it's a no decompression limit, okay? But you might think, well, if I can get this to 0 by breathing 100% oxygen, why wouldn't I just do that, right? If I can make this 0 and I would have no decompression limit at all. Well, that's one of the hazards of oxygen, right? At certain partial pressures of oxygen, oxygen can become toxic, and it's one of the biggest hazards of diving with oxygen, right? At about a 1.6, the industry limit, contingency limit for oxygen is 1.6. Above 1.6, you're in a dangerous spot where you can start going into convulsions. In fact, 1.6 is a contingency limit. It's like going 80 miles an hour in a 70 mile per hour zone, right? 1.4 is going 70 miles per hour in a 70 mile per hour zone. You know you're not going to get a speeding ticket, right? So if you are doing here, you're at your contingency limit, right? If you start going into convulsions, it's called CNS oxygen toxicity. The oxygen attacks your central nervous system and you start going into convulsions. If you're on the surface, it's not a big deal. If you're underwater, you could spit your regulator out and you drowned, right? It is one of the single most hazards, dangerous hazards to a diver in the sport diving community, right? That is like super deadly. It's right up there with AGEs and holding your breath going up while you're diving, right? So you have to manage this risk, right? As we have no decompression limits, that's how we manage our exposure to nitrogen. We have another operational aid to managing